So today's video is just going to talk about refraction specifically in terms of our wave behaviors. Now refraction is something that we've experienced many times before whenever we put a straw into a glass, whenever we've looked through a glass of water at a different picture behind it and it looks different, whenever we've seen a rainbow, and in a pool whenever things seem to be in a different location than you would expect them to be. And that's all because of this property of refraction. So looking at a straight log in the water, or a straw, we can see it bend at the boundary of the water. Now this is dealing specifically with light and how it bends, but we're going to look at it from the aspect of just mechanical waves. Light will cover when we talk more about that in optics. So in terms of mechanical waves though, behavior happens the same way. We see the same bending of the wave. Some of it's been reflected, and we see the refraction of the wave through the boundary, much like we see here. When that happens, we do have some of the properties of the wave change. And specifically, what we see change is related to what type of change the boundary is. So when waves approach a different medium, they're going to bend, and this is called refraction. It's what makes a lot of things work, like the glasses, contact lenses, microscopes, telescopes, anything like that where light is going through it works on refraction. Again, we're going to focus on it for any wave, not just for light, because it does happen for any wave. So going from to a slower medium, we've got our regular wave, where this is our wavelength, and we've got our angle of incidence towards that boundary. After, on the other side of the boundary, we have a noticeably shorter wavelength. We've got a smaller angle, as well as it will look like it's going slower, and we're going to see that in this simulation. So we can see the wave coming at the boundary of the aqua and dark blue. We see a smaller wave going much slower on the other side. So we can summarize that in terms of the wave speed slowing down for a faster to slower medium. The wavelength gets shorter, but the frequency ends up staying the same. And the reason that works is because of our equation. The frequency is the speed over the wavelength. If they both decrease, the ratio of those two will still be the same, which means the frequency results in the same. So the same amount of waves pass you every second, regardless of the medium. And that's good for a lot of different waves, and we can see how that works. The direction that it's going to bend is very predictable as well. So if it's going to a slower medium, that angle of refraction will be smaller than the angle of incidence. And we can see that in action here. So we've got it going into the boundary, and we see it bending away from the normal. So we would be going along this line here. This is the direction of the wave in this situation. And then here, it bends and starts heading a slightly different direction. And that's what we can see for light. The same thing happens for water waves if they're going into shallower water. But then we can also think of the reverse being true. So in terms of going from a slower medium to a faster medium, everything is essentially the opposite. So being implied that it's a faster medium, the wave speeds up. So this is like being in the water looking outside towards the air. And so the wave speeds up and the wavelength gets longer, and the frequency again stays the same because that ratio of those two will be the same, and the direction of the wave will bend away from the normal, resulting in a larger angle of refraction compared to the angle of incidence. And we can see that here, now that we've got our wave in the slower medium going into the faster medium, the wavelength gets longer. It looks like it's speeding up, and you can see that dramatically on the right side. It's going much faster. And then some crazy things start happening with the interference, and it looks like there's periods of absolutely no wave based on the way that it's just spreading out. And that is, certainly a lot more complicated, as is all of the interference that's going on in this area down here. But this, again, it's just trying to visualize the changes in the wave properties, but the frequency stays the same, the wavelength gets longer, and the speed gets faster if we're going to a faster medium. So that would be like going shallow water to deep water, or from inside water out to air, for something like sound or light. The good thing about the frequency staying the same is sound is all about different frequencies. So the sounds in different mediums are the same. So that's it for refraction. There will be one other video for this section focused on diffraction. But as always, physics is awesome.